Welcome to EMILAC Online tutorial. Now before us is this question that we're told to find the dimensional formulas of a universal gravitational constant G, coefficient of viscosity, thermal conductivity, electric potential, and specific heat capacity. Alright, let us start with universal gravitational constant. Now let us recall that according to Newton's gravitational law, you have that G, which is the gravitational constant, now is the product of both the m1 and m2 all over the distance, the square of the distance of separation. Alright, first of all, let us make G the subject of relation here. And when we make G the subject of relation, here we have that FR squared all over m1 m2. Now breaking this further, now let us find the unit of this parameter. Now for F, you have what? Kilogram meter per second, then times meter square all over kilogram times what? Kilogram. Alright, now after which we will now plug in the dimensions of all these units. Now putting the dimension of kilogram here we have the m. Now for meter we have the length, for second we have the time. Now for another meter we have length square, then all over 2 kilogram, which is what? M times m. Okay, now we can now eliminate this, we cancel this m, then here we are left with L times L square will give us what? L is to the power of 3, then T raised to the power of minus 1, then we have m raised to the power of what? Minus 1. So the dimensional formula for our gravitational constant, you can just rearrange this to be m minus 1, L raised to the power of 3, and T raised to the power of what? Minus 1. This is the dimensional formula of gravitational constant. Now let us move to coefficient of viscosity. Now let us also recall, let me use this place, that F now equals to then A dv all over dx. Okay, now and to doing this, now you can also write this as F equals to the coefficient of viscosity, then area times velocity all over the displacement. Now making the coefficient of viscosity the subject of relation, now here we have that F x then all over a v. All right, now putting this in their units, then here we have that the force kilogram meter second square per second square, then times meter, then all over area, which is in meter square, then velocity, which is meter per second. Okay, now bringing this also, now dimension of all these, then we have that the kilogram is in mass, then the meter here is the length. Now the second per second square, here we have T raised to the power minus 2, then another length, that's in meter, then all over another length here and another length here, which is what? L raised to the power of 3, then the time, that seconds, we have what? T raised to the power of minus 1. Okay, we can now eliminate. So here we have then the mass. Now this is raised to the power of 3, and here we have raised to the power of 2. Now if we to eliminate this, so we are left with 1, and here you have T raised to the power minus 1, then minus, according to the law of indices, minus 1. Since this is dividing this, so the 2 raised to the power of minus 2 minus, which is division sign, then minus 1 will give us this. So our L here in terms of indices becomes minus 1. Now let us recall, according to law of indices, that 1 over a equals what? A raised to the power minus 1, and that is what I've done here. So here we have that m, then here we have t raised to the power of, here becomes minus times minus will give us plus, so minus 2 plus 1 will give us what? Minus 1. Then l raised to the power what? Minus 1. Now this is the dimensional formula of the coefficient of viscosity. Now the next one is the thermal conductivity. And when we come to thermal conductivity, we know that Q equals to Ka, then change in let me just put it as temperature, then all over the distance T, sorry, that is displacement, that will be X. Okay, so with this, now let us now make a K, which is the thermal conductivity, the subject of relation. So here we have that K then equals Qx, then all over our A, now the temperature and time. Okay, now with this, now let us now convert this to their various units. Now let's take note that the quantity of heat here is the same thing as the work, and which means our work here is what? Force times what? Distance. Okay, so here we have that K now will give us force times, let us represent the distance as x, so x times x all over the area, then the temperature times time. Okay, now our unit here, so here we have that K now will be, our unit for force here will now be kilogram meter per second square, now times meter all over area, meter times meter, that is meter square, then the unit of temperature here is Kelvin, then times seconds. Now converting this now to their dimensions, so here we have the kilogram is in mass, then the meter here L, the seconds here will be T raised to the power minus 2, then here we have another L times L all over, let us put this in any dimension, that will be L times L, then times K, then times time. So after which, now we tend to eliminate this, we eliminate this, we eliminate this. Okay, so we are left with that K equals that K. Now after cancelling this and this, here you have M, L, then T raised to the power minus 2. Now take note that this is T raised to the power of 1. So here you have, because of the division sign, minus, then 1, which is this, because T, 1 over T equals what? T raised to the power minus 1. So here we have also K raised to the power minus 1. So our K here, which is the conductivity, we have M, L, T raised to the power minus 3, then Q raised to the power minus 1. This is the final answer. Okay, now let's move to number 4. Now for number 4, the electrical potential. Now let us recall that work done equals Q times the electrical potential. Now if we have to make electrical potential the sort of relation, we have that V equals to work done all over the charge. And we know that for the work done, it is force times distance, then the charge is the current times time. Okay, now putting this to their unit, so here we have the force, that will be kilogram meter per second square, then times the distance, which is in meter, then all over current, which is in ampere, then time, which is in second. Okay, now dimensionally let us replace all these units. So here for kilogram, we have that this is m, the capital mass, then m, the small meter for length, then the time, the seconds for the time, and another length all over. Now the current, which is the ampere, also represented as A, or some it can also be represented as I. Then for the seconds it is T. Okay, now here we have the V then equals to M. Now L times L, you have L raised to the power of 2. Then here you have T raised to the power minus 1, then minus 1, which is this, then A raised to the power minus 1. Okay, so our V here will give us M, then L raised to the power of 2, T raised to the power of minus 3, and A raised to the power of what? Minus 1. Now this is the dimensional formula of electrical potential. Okay, now let us now move on to the specific heat capacity. Now let us recall that Q equals to MC then theta. Okay, now after which we make C the subject of formula, which becomes that C equals to, when we divide both sides, so here we have Q all over M theta. Okay, now we know that this quantity of heat here is the work done, so here you have force times distance all over then the M theta. Now for the unit here you have kilogram meter per second square times meter, which is the unit of distance, then mass kilogram, then temperature, that will be Kelvin. Now the dimension here we have meter for kilogram, sorry, mass for kilogram, then length for meter, then time for second, and another length for meter all over mass, then and Kelvin, which is the K for dimension for temperature. You can also probably use this as the dimension also, but in this video we're using K. So here now we can eliminate this, so C, we are now left with L times L, you have what? L raised to the power of 2, then T raised to the power minus 2, then our K here, which is a denominator, can be transformed, become an indices minus 1. So this is the dimensional formula for specific heat capacity. Alright, so now this is the final solutions to this dimensional analysis of this quantity. And if you love what I've just done, kindly subscribe to my YouTube channel and ensure you click on the notification button to be notified of all my videos in physics and mathematics. Thank you and God bless you.